This is the presentation of the paper Efficient Video Prediction via Sparsely Conditioned Flow Matching done by Aram Davtyan, Separ Semeni, and Paulo Favaro at the Computer Vision Group at the University of Bern. Video prediction is the task of predicting future frames given past ones. It is a fundamental component of many applications, especially in robotics, where an agent needs to interact with the environment. This capability enables planning and advanced reasoning, especially when other agents are in the scene. More in general, however, a video prediction model that can generalize to new unseen scenarios needs to implicitly understand the scene, which means to detect and classify objects, learn how they move and interact, estimate the 3D shape and location of the objects, model the laws of physics of the environment, and so on. In addition to naturally leading to rich and powerful representations of videos, this task does not require any labeling and thus is an excellent candidate for learning from readily available, unannotated datasets. More formally, the task of video prediction can be cast to modeling the following conditional distribution of the upcoming n frames given the first k frames. This distribution can be naturally decomposed into the product of n one-step predictive conditional distributions. This decomposition that we stick to in this work suggests an autoregressive sampling of the future frames. This is not the only option. For instance, one could also predict more than one frame at a time. However, explicitly conditioning the next frame on all the past frames is computationally and memory-wise demanding. The reason for that is that, with no additional assumptions on how the frames are generated, the conditioning grows with the number of frames, and each X in the conditioning input is an image, so the input soon becomes a huge tensor working with which is unfeasible. If we plot the prior work on the FBD versus training compute plot, we will observe a natural trade-off between the quality or accuracy of the models and the computational requirements of training. The models on the faster side produce low-quality videos, while the ones that generate high-quality videos usually require a significant amount of compute. So ideally, we would like to end up in the region of the plot where a model is both efficient to train and generates realistic and accurate videos. In this work, we propose such a model. We call it River for Random Frame Conditioned Flow Integration for Video Prediction. River achieves superior or on par performance compared to prior work on common video prediction benchmarks, while requiring an order of magnitude fewer computational resources. Here you can see that River is able to generate smooth and realistic videos, while prior work struggles to model the dynamics of the scene. In summary, the key design components that make it possible are the following. As a training objective, we use flow matching, a simpler, more general and faster alternative to diffusion models. River operates in the latent space of pre-trained VQGAN to further reduce computational complexity of the task and allow for generation of high-resolution videos at the same costs. But most importantly, we propose so-called distributed past modeling for dealing with the computational complexity of conditioning on the past frames. With this technique, we condition only on a small randomly sampled set of frames at each denoising step of flow matching. Let's have a look how River is trained in a step-by-step manner. First, the target frame is randomly chosen from a sample video. A noise observation is produced by adding a predefined amount of noise according to the flow matching objective. The previous reference frame as well as a context frame randomly chosen from the past are fed to the model that is trained to regress the denoising step at the corresponding point. Notice that only 3 frames are used for training, so we don't need to store and process the whole video. At inference, when the task is to predict next frame xt in a video, one needs to start from a random noise and iteratively denoise it toward the clean image. At each denoising step, the previous frame xt-1 and a randomly chosen context frame xt from the past are fed to the model to predict the denoising step. This is repeated till the clean image is obtained. Notice that at each denoising step a new context frame is sampled. This way the model is able to implicitly observe the whole past, while keeping the relation cost constant. We test River on several video prediction benchmarks and show that on the bare dataset, River reaches a trade-off between the FBD and the compute, and is able to generate smooth, realistic videos while requiring much less computational effort. Furthermore, although the standard benchmark on bare uses 64 by 64 resolution images, with the help of the perceptual compression, we are able to generate high-resolution videos under the same training costs. The videos showed on this slide are of 256 by 256 resolution. On the KTH dataset, River generates structured human motion and achieves state-of-the-art performance compared to prior methods that do not use domain-specific help. Thank you for your attention. Check the paper and visit our project page for more details.